Hello, and thank you for joining me today. My name is Mike Simmons, and I am with Intelivation. And today I'm going to be talking about advances in precision optical coatings produced by roll-to-roll vacuum web coating. I'll start by telling you a little bit about Intelivation, and then I'll go over the background of optical thin film coatings. I'll review the equipment setup that we use for the work presented here. And then we'll demonstrate three complex multi-layer optical coatings produced in roll-to-roll format. We'll go over the coating spectral data and curve fits, and then summarize. Intelivation is an engineering and process-centric equipment company, which was founded in 2009. We have an emphasis on innovation, and we are located in Loveland, Colorado, here in the United States. We manufacture roll-to-roll coating equipment. We have innovative roll-to-roll systems up to about 2 meters wide. And we also offer advanced process technology and monitoring components, things like reactive sputter control, magnetrons, advanced magnetics, sputtering magnetic materials, substrate pretreatment, in situ monitoring. We are a vertically integrated company. We're located in a 21,000 square foot facility. You can see a picture of it here. We just moved into this facility last year, just as the pandemic was underway. And we have on-site engineering, machining, fabrication, and assembly. We also operate an application lab where we're able to do process development and demonstration for customers before they purchase their own tool. So what do I mean by precision optical thin film coatings? I'm talking about coatings that perform a wide range of functions, things like anti-reflective coatings, in some cases decorative coatings, coatings also used for security, perhaps identification, passports, solar control films, high energy laser. There are many applications that fall under this umbrella. And a common thread is that these coatings have 2 or more thin film materials in them, often only 2 materials, one with a low index of refraction and one with a high index of refraction. There's other possibilities as well, things like reflectors and absorbers. And the most high-end optical thin film coatings are not produced in roll-to-roll format, at least traditionally they are not. And they are traditionally produced in batch coaters and drum coaters on discrete substrates, individual substrates. Some of the performance drivers for optical coatings are accuracy and precision, being able to control the layer thickness very precisely, being able to deposit a material that has bulk properties that are representative of what the coating design was looking for. So stoichiometry, things like that. And then also the number of materials and the number of layers in the coating design. Over on the right, we have a couple of pictures here of some neat optical coatings. So once again, coming back to applications and then also talking about some equipment requirements, many applications. I won't read through all these listed on this slide here, but wide range of products for a wide range of uses. And in some cases, if you think about energy storage, perhaps not an optical coating in a traditional sense, but a dielectric used in a battery, for example. So in terms of the requirements for the equipment used to create these types of coatings, reactive deposition of oxides, nitrides, oxynitrates at a high rate, precise control of layer thickness, in situ metrology, advanced automation, the ability to deposit multi-layer coatings with numerous layers, and frequently application-specific pretreatment of the substrate, flexibility of the machine. These requirements change over time, and just many requirements for these machines. Now, when we talk about traditional roll-to-roll optical thin film coatings, they were in the past limited to single pass coating. And so, this would be a single direction roll-to-roll coating tool And so that means the number of layers in your coating would be less than or equal to the number of zones in your machine. And so, you know, for practical purposes here, we'll say about 6 layers per coating drum in the machine. And so some of the challenges that occur here are deposition rate matching, for example, and heat load management. So if you have a recipe that calls for a very thick material that's a low deposition rate material, and then a very thin material in general, or a thin high rate material, that creates some challenges in producing that coating. And so for these reasons and others, some of the high-end, high-value applications were excluded from roll-to-roll production. So if we think about modern roll-to-roll optical thin film coatings, you know, we want to overcome those challenges. And so some of the things that we do is we utilize bidirectional, fully reversing web drive systems, fully automated deposition with precise control, reactive sputter control, so that we produce the coating that we intend to be producing at a high deposition rate. And then in situ monitoring as well, so that we can monitor this coating as it's produced. And the ability to operate in both roll-to-roll mode and drum mode is also helpful. We'll talk more about that later. And so this enables a new frontier in roll-to-roll optical coatings, where we have essentially an unlimited number of layers that can be used in the coating stack, and optical designs that now have, instead of up to 6 layers per coating drum, up to 6 materials per coating drum. So the goal here being that to make this possible to produce the high-end, high-value optical coatings in a continuous roll-to-roll format. So we're going to demonstrate some complex roll-to-roll optical coatings, and we're going to do this on a roll-to-roll platform. We're going to use a multi-pass approach. We're going to add passes to manage substrate heat load in some cases. We'll demonstrate that. And we're going to use TiO2 and SiO2, the TiO2 via planar magnetron, SiO2 via dual rotary magnetron. We're going to look at a 22-layer long wave pass coating, and a 6-layer anti-reflective coating, and a 28-layer shortwave pass coating, or hot mirror. The equipment setup we're going to use is an Intelivation Application Lab R2R 330. So this is a tool permanently installed here at our factory, where we do this type of work and do demonstrations. So it's equipped with in situ and ex situ thin film characterization. We also have the drum mode and roll-to-roll mode, fully automated processing, and bidirectional web handling system. The substrate we used in this case is a 5mm PET, and we're using only 2 of the deposition zones in the machine. And so in one zone, we're depositing SiO2 via dual rotary magnetron sputtering in a reactive process. And then in another zone, we're depositing TiO2 via Tiox target. So what do I mean when I talk about multi-pass coating? In this case, what we're going to do is we're going to take 1 layer in the coating design and distribute that across multiple passes just to manage the heat load. And so the way we determine these settings is, first we characterize the dynamic deposition rate in the tool, and then we go through and determine an acceptable heat load for our particular substrate. So by way of example, if we have a DDR of 25 nanometer meter per minute and a layer thickness of 100 nanometers, we calculate the net line speed being 25 divided by 100, or 0.25 meter per minute. We select the number of passes in order to manage the heat load. This is in a lot of cases just determined experimentally. Different substrates behave differently. And then we multiply that speed by the number of passes and run the material through the machine that number of times. And then we repeat that for each layer in the stack. The other thing on this slide is the talking about roll-to-roll mode and drum mode. And so another thing we're able to do is run through all of this characterization in a drum mode, where we attach substrates directly to the drum. And in that case, we can attach things like glass microscope slides or silicon wafers, where we can get better characterization than perhaps on a plastic substrate. And so this is a technique that we find really useful and really accelerates development of coatings. We're also going to utilize automated processing here. And so we're going to enter into the control system some recipe data, heat load data, the position on the web that we want to coat, and some other settings. And then we just press start and walk away, and our coating is made for us. So the first coating we're looking at is a long wave pass filter or a cold mirror. And so the recipe is shown over on the right-hand side of this slide, and you can see the 22 layers alternating TiO2 and SiO2, and you can see the thickness of each layer there. And so we designed this coating with a 550 nanometer cut on, and it has a total thickness of 1.6 micron. We used 91 passes for this particular coating. The cut on placement came in within 0.31% of the design. And if you look at the lower left corner of this slide, you see kind of a neat picture here. So when we did the initial characterization, we coated on microscope slides. And the two pictures in the lower left are actually the same microscope slide. In one case with the lighting such that we're seeing the color in reflection, and in the other case, we're seeing the color in transmission. So that's kind of one of the fun things about these types of coatings. The next coating we looked at was an anti-reflective coating. And so this was a 6-layer coating, 241 nanometer total thickness, so much thinner coating. And we used 24 total passes in this case. And so we were able to reduce the front surface reflection significantly. Our performance matched the design pretty closely. We suspect that the surface coating on the polymer substrate probably explains the discrepancy between our design and our actual performance. The chart over here shows a number of things. The yellow curve is the reflectance of the bare PET. And so we're seeing the reflectance on both the first and the second surface. And the blue curve is the performance after coating. And then the red and the green describe the theoretical maximum performance compared to the actual performance. The next coating we looked at was a shortwave pass filter or a hot mirror. This was a doozy of a coating. It's 28 layers and 4.2 microns thick. So you can see the full recipe over there on the right. This coating did have some pretty thick layers in it. And so we used many passes just to keep the heat load low on the substrate. It was 238 passes altogether. And the cut-on placement was within 1.25% of the design. The coating did have some haze, but it didn't craze or delaminate. And thin film stress did also cause some curling of the substrate. Things like this can be mitigated with further process development. The curve here shows the performance of the coating compared to the design, and you can see the agreement is pretty good. For the hot mirror, we did go ahead and run a test to see kind of how it performs. So we attached a thermocouple to an oven, and on the left there was a thermocouple directly on the oven. The thermocouple reached 109 degrees Celsius. And then we also put the hot mirror coating in front of the facing the oven, and the temperature reduced to 66 degrees. So we certainly see some effectiveness of that coating in that case. So in summary, we reviewed the challenges associated with scaling these complex precision optical coatings from single substrate batch processing to continuous roll-to-roll processing. We generated 3 multi-layer precision optical coating designs to study this, from 6 to 28 layers up to 4.2 micron thickness. We set up the application lab R2R 330 tool to deposit these coatings, and we successfully demonstrated these coatings in roll-to-roll format, utilizing both multipass capability and great accuracy for each layer. And so in summary, we were able to demonstrate these things, and we see some new possibilities enabled by this to help bring costs down on some of these precision optical thin film coatings. If you'd like to learn more about this, feel free to reach out to me. And my contact information is on the slide here. And I'd like to thank you very much for your time. Bye.